So now that we are empowered by all this knowledge about our own human eye. Now let's look at how some of these displays operate. So let's look at LCD display. So if you open up a LCD display, the first thing you see it has lot of layers. It's like human beings are multi-layered personalities. Onions have multiple layers. LCD display has many, many layers and layers and layers of things. So some of the main components are it has a backlight. So this backlight used to be fluorescent, but nowadays almost everybody uses a LED backlight. So and some of these smartphones and tablets, they use a side backlight. Even most of the TVs now, they use a side LEDs. So you'll have a row of LEDs placed on the side of your display, and they will shine light this way, and then you have a diffuser, and that diffuser makes that light uniform and also projects it out in this perpendicular direction. Then the first thing you have, then the next thing you have is polarizer. So if you're using a LCD display, you first need to polarize the light. Then it has to pass through this back plane, which is consisted of these thin film transistors, which are used to drive these liquid crystals. And on top of that, you have this liquid crystal array. And on top of that liquid crystal array, you have a color filter. Then you have another polarizer. And then you have further encapsulation layers. So there are layers and layers of things inside your LCD display. And to give you some more idea how a LCD display works. So these are two different there are two different schemes in which your LCD display can work. One is the most common one, or the older one, is called this twisted pneumatic configuration, or TN configuration. And the way it works is that you have one polarizer, so it will polarize all your light in one particular direction. And then you have liquid crystals stored between these two gates. And when you don't apply any voltage, this liquid crystal essentially has this helical pattern, so it will bend that light into a 90-degree angle as compared to what it came in, and that other polarizer is placed at a 90-degree angle to the first polarizer. So if you apply no voltage across your liquid crystal, that means so if you apply no voltage, it means that your light is on. If you apply a voltage, it orients all these liquid crystals in a particular direction. And these liquid crystals are essentially organic polar molecules. So they have some polarity to them. So whenever you apply a voltage or an electric field, they will orient all in one particular direction. And now they don't bend the light anymore. So the light coming in will maintain its polarization, and since the other polarizer it's at a perpendicular angular to the first one, you won't get any light out of this. So another important thing is that there's no current needed to drive the liquid crystal. So all it needs is a voltage across your liquid crystal, but it does not consume any power to manipulate this liquid crystal. Most of the power consumed in a LCD display is consumed in our backlight. The response time of this is anywhere between, the minimum you get is 2 milliseconds. So the maximum frequency that you can get from a LCD, or just the liquid crystal part of the LCD, is 480 megahertz, 480 hertz. And so there are many pros and cons of this technology. Some of the pros of LCD, and when I'm saying pros, it's compared to an OLED display that we'll cover after this. So if you look at the resolution, you can easily achieve a resolution of above 300. So that's what your iPhone it achieves. It uses a LCD display, and it achieves a resolution of 328 pixel per inch. So it can easily achieve a retina resolution even for a thing which you hold 10 inch away from your face. It's bright, and the brightness is essentially given by the brightness of your backlight. So you can put, there's no limitation on how bright a backlight you can put. If you're putting it in a mobile device, of course, it will drain out your battery, but there's some displays from Nokia which achieved up to 100, not 100, 1,000 candela per meter square. And this candela per meter square is essentially, it's the unit of your luminosity, and what it means is one candela means one candle shining, and you're holding it 1 meter away, and that light is falling at a square feature which is also the same dimension. So 1,000 candela per meter square means 1,000 of these candles shining in 1 meter square of space, and that's quite a lot of candles. So these displays can get very bright. Another thing is it's a mature technology, so it's very low cost, but it comes with a lot of disadvantages. One is that the maximum contrast you can get is limited. So that iPhone that I talked about, it has only a contrast of 800 to 1. And that has to do with the fact that your light will essentially comes in. And the way this thing is turned off is you try to bend that light 90 degrees so that it does not leak out of that upper polarizer. But there's always some light which always leaks out. So these liquid crystal, they're not perfect switches, so they always leak out some light. They can't completely change their polarization by 100%. So that limits your contrast. So your contrast in your LCD display is limited by these gray blacks. So these blacks are not completely black because there's still some light leaking out. And again, there are many, many layers, and each of these layers will, which will transmit only a fraction of your light, and it will reflect a percentage of your light back. So overall, what your backlight, if you say start from 100 photons from your backlight, you are only able to get 5% through your top, get it out of your display. So this, not taking into account the efficiency of your backlight, your efficiency of just your LCD module is 5%. And these backlight typically have an efficiency of 20%, or it uses a LED, so those have an efficiency of around 20%. So overall, your efficiency of your overall display, your power input versus light output is 20% of this 5%. So overall, your LCD display is less than 1% of your light is converted into, less than 1% of your power is finally comes out as light from this display. Another thing is it has very poor viewing angle. So if any of you has used, even in your TV, if it's a LCD TV and you view it as at an angle, it has a very poor viewing angle, and a lot of it has to do with is that your backlight is, it's placed at the very bottom, and by the time the light comes out, it's already very directional. So your light which comes out has a lot of directionality to it, so it has poor viewing angle. It also has a very poor, not very, but poor color gamut, and the way you can increase your color gamut in a LCD display is to make your red, green, and blue color filters more dark, or make them more colorful. But that always limits the amount of light that passes through. So there's a color versus power trade-off in this device. So you can get a larger color gamut, but then you'll get lower power efficiency. And the final trade-off is, the backlight. Even if you have dim images, your backlight is always on. So that's another trade-off. So recent advancement that has taken in this field is this IPS technology, or as we saw in that iPhone 4 announcement, it says IPS LCD. So what does that IPS stand for? So IPS stands for in-plane switching. So traditionally, these two electrodes which contain your liquid crystal, the one used to be placed in the bottom, and the other one which was conductive or made of, both of them are conductive, but made of, say, ITO or zinc oxide or some material of similar transparent conductive material. They were placed one on the top and one on the bottom. The recent advancement that has taken place is that these two conductors are placed both at the bottom, and it's called in-plane switching. It comes with the disadvantage that you have two of these wires running through your in the path of your light, so that degrades your fill factor, which stands for how much of your area is occupied by this wiring. So it degrades your fill factor. What it improves is that now you have one less layer on the top. It also improves your viewing angle and your gamma, because since you have less layers, also you can reduce the directionality of your light. Also, if you press it from the top, it does not produce any tailing. So this is currently used in all the iPhone 4 forward. All displays, smartphone displays use this IPS technology. So as I mentioned, your LCD display degrades very fast if you go at an angle. So if you look at exactly normal to it, it has a contrast of 800 or a maximum of 1000. If you look at just 30 degrees angle away from it, that contrast reduces to 400. And minimum contrast you can distinguish as 10 to 1. But if you go below 400 to 1, your quality really degrades. So that's what a traditional TN or a perpendicular scheme would give you. In-plane switching schemes, it tries to improve your angle from 40 to 70 to 120. So if you have an iPhone first generation versus fourth generation, you'll find that your fourth generation has a much better viewing angle, and a lot of it has to do with this in-plane switching technology. Any questions on this? So the next thing I want to talk about is OLEDs and displays using OLEDs. And if you open up a OLED display, and most of your Samsung smartphones would have a OLED display, it looks much more simple as compared to your LCD display. So first of all, it has much less layers. So it has very simple personality. It has only two layers. One is related to your TFT backplane. So it has one layer which is full of these transistors which control the voltage and current to each of these LEDs. And the top layer is very simple again. It's just these three OLEDs of different colors, and that's all. So you have a TFT backplane which controls the signal, and that's why it's called active matrix, because you can control each of these LEDs individually, and on top you have these light emitting diodes, and that's it. So you have just two layers. Sometimes people put a polarizer on the top to cut the reflected light, but it just has these very simple structure with just two layers. So what are the advantages of using OLED display? There are many advantages. One is that it's thinner, and people have made, since it's just two layers, you can make it very, very thin, and people have made these displays which are just 300 nanometer thick or just 0.3 micron thick. It has a very large color gamut, and that comes from the fact that it has these three individual LEDs, and you don't get white light and then passes through a color filter, but you're generating these three very pure primaries, and that gives you a large color gamut. It has a very high contrast ratio. And why is this contrast ratio higher? The contrast ratio is higher because black has essentially zero intensity. Black is completely black. The way you get black in an OLED is you just turn off both three of your LEDs, and what you get is black. So black essentially has no intensity in your in your OLED. So even though your white or the brightest you can get is low, your black is really black, and that drives your contrast ratio very high. Any of you who has worked on LEDs know that you can switch them very fast. So you can switch these OLEDs at a switching time of 0.01 millisecond, and that gives you, a frequency of 10 to power 5, which is definitely more than what, I think more than what human eye can perceive. So another thing, it has very less layers, and the light is being generated from the very top layer. The light is being generated from that OLED layer, which is at the very top. So it has better viewing angle as compared to LCD. It is flexible. You can make it on flexible substrate. In principle, it can be low power, and it can be low cost. But it comes with a lot of disadvantages. You have, it's less bright, and a lot of it is limited currently by the efficiency of these OLEDs. These OLEDs operate, these red and the green OLEDs operate at an efficiency of 20%. The blue one operates at an efficiency of only 4%. And that limits your overall brightness. Your resolution, as we'll just talk, it's again a technological limitation, not a fundamental limitation. It's right now limited to 300 pixel per inch. Also, these blue LEDs, they degrade with time. All these OLEDs degrade with time, blue in particular, and your overall display quality degrades with time. So these comes with a, a life time of, they say around 5 years if you operate it continuously for 8 hours a day. So, which is the requirement that you have on most of your television. Your blue, though, degrades much faster than the other one. That's why you intentionally shift your white balance to blue side when you ship the display. So when you ship the display, you ship it with a white balance of centered around 7,500 Kelvin, because your blue is known to degrade over time. Currently, they are not as low power as I'll just show you, and they are not low cost either. Another thing is the maximum size is limited currently, and in fact, it's most prevalently used only in your smartphones. You have a cathode, which is a material with low work function. They use things like barium, calcium. You have two of these layers. One is electron transport layer. Then you have a hole transport layer. And then you have an anode, which is transparent. So it's typically made of something called indium tin oxide, which by good fortune also has a high work function. So this high work function layer can easily supply holes. That low work function cathode can easily supply electrons, and they come and combine and generate light. And the way you tune what light is being generated is by choosing the different organic materials for these layers. So there are, a large variety of materials available, but this is what they typically use for. So they use a different molecule for blue light, they use a different molecule for green light, and they use a different molecule for red light. Don't ask me what they exactly are, but so you use 3 different molecules for making this. Using these 3 different molecules is essentially what limits your resolution. So since you have to use 3 different of these molecules, and you want to place them side by side, currently the way they are manufactured is they use this technology, very sophisticated technology of evaporation and fine metal mask. If anybody of you has worked in a lab, this is essentially same as using a shadow mask, and that's not very high tech. But any of your shadow mask technology, it has a limited resolution that you can place 2 of these adjacent features on side by side. And currently, the maximum resolution that you can achieve between these 2 red and green and blue is the minimum feature size that you can keep between them is 15 micron, and that gives you a resolution of around 200 pixel per inch. So it's more of a technological limitation, and people are working around it. So to get it to a retina resolution, a lot of things have been worked around. The most promising thing it looks like is which people are starting to use, and Samsung just announced some displays using this, is laser imaging. So what you do in that is you have these layers of dyes that you want to print, and then you scan it with a laser, and that deposits that layer. And you could have a roll process for your laser, so it could be fast as well. And this is not the only option. People are looking at multiple of these technologies. You could do a lithography, but again, that would give you a good resolution, but it would be expensive. You could do a roll printing, but that again doesn't give you very high resolution, but it could be very high throughput, so you could make them very cheap. You could do a vapor jet printing that gives you somewhere in between resolution, but it's again not very fast. So these are all things that are being currently cooked up in pilot lines. But in between, so what have been people doing in between right now? Samsung has been shipping it for a while, and they claim it's a retina display as well. So what they have been doing is they have been leveraging our knowledge of our human vision and fooling around our eye. And I highly encourage you to do this as an exercise. If you have access to a microscope, either inside SNF or in your lab, take your iPhone and take a Samsung phone, and just look it under a microscope. iPhone would look like this, and a Samsung phone would look like this. So what they have is in a LCD display which you have in your iPhone, you'll see a very regular array of red, blue, and green. If you look it up in AMOLED display, that OLED display that Samsung ships, it would have twice the number of greens, and these green pixels would be actually smaller, and it would have half the number of blue and greens. So this is your legacy RGB display. It has six of these columns, or 3 columns for each black and white layer, or 6 columns for a pair. What Samsung does for their OLEDs is they use this thing called pentile technology. It was developed by a company here in Cupertino. And what they do is they essentially they bring this much closer, but they only have half the number of blue and red, but they have twice the number of greens. And they leverage this fact that our human eye is much more sensitive to green, so it makes sense to have much more of these green pixels. Sometimes they even, so these are all these displays, and there's a name for these displays. They're called biomimetic display, or this is a very generic name for technologies that imitate our human vision, and there are similar technologies available for audio as well, and which try to emulate how our brains are wired for vision and for sound. And the way they do it is that you have twice the number of green pixels, and there's even a next generation technology which is RGB white. So some of these OLEDs have less intensity because the LEDs organic LEDs have less efficiency, so they include a white pixel adjacent to them as well. So it becomes a RGBW, W standing for white, and that way they try to make up for the brightness. So there's a lot of interesting stuff that people do on the system level to make up for the handicap of your organic LED. Another trick that people play at a system level is that your blue pixel, it degrades very fast with because these blue pixel, first of all, it has low efficiency, and if you flow a large current density through it, it degrades very fast. So what they do is they make the blue pixel much larger, so the current density through it decreases, and it degrades less fast. And there's a company called Ignace which licenses this technology. So your blue pixel has larger area and less current. Some of the Samsung displays are using this currently. So it's very interesting actually. If you look up your Samsung display under a microscope, you might find either this or that or a mixture of these, but it's very interesting to look it up under a microscope.